In this video, I will discuss some JEE Main PYQs from the topic gravitation. These questions have appeared between the years 2023 and 2022. Timestamps are given in the description box. You can watch parts of video if you are running short of time. I will discuss some 5 questions. This is the first one. The escape velocities of two planets A and B are in the ratio 1:2. If the ratio of their radii respectively is 1:3, then the ratio of acceleration due to gravity of the planet A to the acceleration of gravity of planet B will be. You can pause and run this question. So first we need the concept of escape velocity. So there is a planet of mass m and there is a small mass say m. So this mass should be given a velocity so that this mass keeps going on and does not come back. So this minimum velocity which should be given to this small m so that it keeps going on without turning back is called the escape velocity. So what should happen is, in the final case, so this m should have reached very large distance, d is approximately infinity, and this velocity is approximately 0, but is towards away from the central charge, central mass, so that it keeps going on. So the energy of the system will be conserved because there is no dissipation. So the initial energy is the gravitational potential energy, which is given as minus g, product of the two masses, divided by the distance. The distance between these two masses is this radius r of this capital M, plus kinetic energy of the small m. There are two forms of energy: kinetic energy of the small mass, because the big mass is at rest, and the potential energy of the interaction between the two masses. And the final energy so the gravitational potential energy is minus gm by the distance, which is infinite, so this term is 0. And kinetic energy of this one, that's also 0 approximately. In the limit, it will be 0. So that means the initial energy should also be 0. So from this, I get the escape velocity as m will cancel. This will go on that side. So 2 gm by r square root. And I can also use this concept of g, which is force on 1 kg, just g into m into 1 divided by the distance square. So gm by r content plus g into small r. So this escape velocity will become gm by r is nothing but g into r. Actually, these two are formulas. So if you can remember the formula, you can straight away use this. There's no need to derive. So using this, we can solve this question. So from this, I get the ratio of the escape velocities: VE1, VE2, second planet, square equal to, I can square both sides, G1 by G2 into R1 by R2. So escape velocity ratio is given as half. So 1 by 2 square equal to G1 by G2 has to be found out. The ratio of the radii is 1 by 3. So the G ratio is 3 by 4. It matches with option 4. 4 is the correct answer. This would explain here. The planet has got mass m, the small mass m, and for it to escape this thing, minimum velocity required is v. So the energy of the system is gravitational potential is minus g, product of the masses divided by the distance, which is r here, the radius of the capital M. M is very small, and the kinetic energy is half m v square. Capital M is at rest. So when this thing goes very, very far away, approximately infinite, this velocity should tend to 0. So here in this case, gravitational potential is minus g mm by distance, which is infinite, so it's 0. And kinetic energy is half m v square, which is also 0. So final energy of the system is 0. So initial energy should also be 0. So from this I get the escape velocity as this one. And using the concept of g, which is force on 1 kg, we'll get g as g mm by r square. The g is on the surface. So using this thing here, we get the formula for escape velocity as square root of 2g r. If you remember the formula, you can straight away use this one. This is the formula. So from this, I get the ratio of the escape velocities as square root of the ratio of g into r. Or I can square it and get the ratio of the escape velocity squares equal to ratio of g into ratio of r. The ratio of escape velocity is half given in the question. The ratio of the radius 1/3, that's also given in the question. From this, I get ratio of g as 3/4. This is the next question. If the gravitational field in space is given as minus k by r square, taking the reference point as to be r equal to 2 centimeter, with gravitational potential V equal to 10 joule by kg, find the gravitational potential at r equal to 3 in SI units, given k equal to 6 joule centimeter per kg. And pause and run this question. Gravitational field is nothing but G, which is force on 1 kg. It's minus k by r square. So r equal to 2 centimeter, it's here, and this is r equal to 3 centimeter. So we can find out the work done to move from this point to this point. Work done to move from r equal to 2 to 3. Its integral f dot ds shall be dr, because we are moving along the direction of r cap. That should be equal to increasing the potential, the final potential at point 3 minus the potential at point 2, or r equal to 2 centimeters. So this force is minus k by r square. So if you integrate this, it will become r is equal to minus 1 by minus 1. Between the limits, you are moving from 2 to 3. So r equal to 2 to 3. So this one will become 1 by 2 minus 1 by 3. This is in centimeter. So here if there is centimeter, will cancel. Here there is 1 centimeter. So this also centimeter. Those two will cancel. So this will give k is 6, and this one is 1 by 6. 3 minus 2 is 1, and the denominator is 6. That's equal to V3. You have to find out. And V2 is reference. Value is 10 in SI units. So this means V3 is 11. Here there is one thing you should be careful about regarding the sign. The force here, to be more appropriate, we should have given this direction as r cap. So force is toward the center. So to move from 2 to 3, work has to be done on the system. So this quantity should turn out to be positive. So here it is positive only. Here there is an external force you have to apply here to push this thing, which will cancel this G. So the direction of the external force is r cap, and this displacement also along r cap. So this angle between these two is cos 0, which is 1. So that's why there is no minus sign here. So we can fix this sign confusion physically, by physical reasoning. Here they are given this force as r cap, so it's towards the center. So to move from 2 to 3, work has to be done on the system to overcome this attractive force towards the center. So this quantity has to be positive. So this organ has to be positive, which is true here. That should increase the potential. So when work is done on the system, potential will increase. So final potential should be more than initial potential. So this is a positive quantity. So left hand should also be positive. Correct answer is option 2, which is 11. So 11 is the correct answer. So this was solved here. The gravitational field is given as minus k by r square, but they should given the direction as r cap. So work done to move from 2 to 3. Since the force is towards the center, so work has to be done. So this has to be a positive quantity. It's integral f dot ds, and this f was the external force acting on the system. So the external force will oppose this one. It will be along the direction of r cap. So g dot r dr will be positive quantity. So work done on system will increase the potential. V3 minus V2. This is a positive quantity. V3 is greater than V2. So here if you integrate this one, I'll get minus 1 by r. Put the limits 2 to 3. So I'll get V3 equal to 11. Next question. A body of weight W is projected vertically upwards from Earth's surface to reach a height above the Earth, which is equal to 9 times radius of Earth. The weight of the body at that height will be. This is a simple question. You just have to understand what weight means. Weight of object is force between two objects by distance square. In the first case, it's thrown from the surface of Earth, so the distance between, in the first case, the mass is like this. So the distance between these two is the radius of this Earth. This is a very small mass, so this distance we can neglect. So the distance from here to here is same as the distance between here and this point, because this is a very small distance. So this is radius of Earth. In the second case, this height of the small mass is increased. Height is from the surface of the Earth 9 times the radius of the Earth. So that means the distance between the Earth and this test mass will be 10r. So in the second case, W2 masses are same, but the distance has increased to 10r. Height above the Earth's surface is 9r, so the distance is 9r plus this distance, which is r, and square, distance square. So from this I get W2 as, so the force will go down, so the weight is going down, W by 100. Take 10 outside, this is same as this one. So the weight has gone down by a factor 1 by 100. Option 2. Is the correct answer. So weight of a mass m is the gravitational force on this mass and the source mass. Here is the Earth. So in the first case, the small mass is kept on the surface of the Earth. So the distance between the two masses is approximately the radius of the Earth. In the second case, the small mass is pushed to a height of 9r. So distance of this small mass from the center of this big mass is 9r plus 1r, which is 10r. So the weight is going down by a factor 1 by 100. Next question. 4 spheres, each of mass small m, form a square of side D, as shown in the figure. A fifth sphere of mass capital M is situated at the center of the square. The total gravitational potential energy of the system is. You can pause and run this question. So potential energy of system of point masses or spherical mass is the energy of these interactions. So there is one interaction like this. We have to find all the pairs, all possible pairs. Each pair will have an energy which is equal to G into the two masses M1, M2 by the distance R12 minus. And you have to sum all this energy of these interactions. So here in this case, I can number this mass as 1, 2, 3, 4th mass, and the 5th one is the central one. So the interactions are this 1, 2, 3, 4, and there will be interaction between this and this, and there will be interaction between this and this, and there will be interaction between this and this, interaction between this and this, and the interaction between this and this mass, and there will be interaction between this one and then this mass. So 4 sides, 4 short diagonals, corner in the center, and then 2 long diagonals. So basically there are 5 masses. So the number of pairs which one can get is 5C2. You have to choose 2 out of to form a pair out of the 5. So that will be 5 into 4 by 2 into 1. If you know mathematics, you can understand this notation. So this is 20 or 10. So there are 10 interactions. So 4 sides, 4 short diagonals, 8, and then 2 long diagonals, 10. So the energy of the interaction 1, 2, U 1, 2 is minus G. The product of the masses is m square, and the distance is d square. And the interaction between the corner and the middle point, say for example 1 and 5, is minus G. Product of the masses is G into m divided by the distance square. So this is d, this is d. So the whole thing is root 2 times d. Half of that is d by root 2. These things are standard things. Square 90 degrees. This is d, this is d. So the full diagonal is root 2 times d. It's more than d and it's root 2 times d. Half of that is d root 2 by 2, which is d by root 2. And the long diagonal interaction is u 1, 3. Product of the masses is m square, m into m, and the distance is root 2 times d whole square. So interactions like 1, 2 is 4 of them are there. So to get the total energy of the system, this has to be multiplied 4 times. 4 such interactions are there, corresponding to 4 sides. And this 1 and 5, again there are 4 interactions of that type. Short diagonals, corner and the center, 4 of them. And there are 2 long diagonals, so this into 2. So totally I'm getting 10 interactions. So I have to add all this thing. So what is common is, it's not d square, it's just d. Potential energy is G into product of the mass divided by the distance with the minus sign. So G m by d is common. So 4 times m, and here will be root 2. So 4 root 2 times capital M. And the third one is 2 by, so root 2 times small m plus root 2 times small m. So minus gm by d. So this is 4 plus root 2 into m plus 4 root 2 times m. A is the correct option. Potential energy of system of masses is potential energy of all the interacting pairs. A is the correct option. So of this 5 masses, the number of pairs we can pick is 5C2. That is 5 into 4 by 2 into 1, that's 10. So basically this mass will interact with this one, and this one. And fourth one is this one, this long diagonal. So since there are 5 masses, each mass will have 4 interactions with the other 4. So you can see this one as well, everything has got 4 interactions. Even the middle one has got 4 interactions. So one type of interaction is this sides. Second type is between this corner and this middle point, 4 of them. And the last type of interaction is the long diagonal. So U12, G m square by d square, this one. 4 such interactions are there, corresponding to 4 sides. And then U15, interaction between the corner and the middle mass, minus gm by d, which is d by root 2. This is the fourth, the long diagonal is root 2 times d. Half of that is d by root 2. 4 of them are there. And u13, the long diagonal is gm square by d root 2. 2 of them are there. 2 long diagonals. So total energy is the sum of these with these numbers put here. So this is the answer. Next question. 3 identical particles ABC of mass 100 kg each are placed in a straight line with AB equal to BC equal to 13 meters. Gravitational force of the fourth particle P of same mass is F when placed at a distance 13 meter from the particle B on the perpendicular bisector of line AC. The value of F will approximately be. First, draw a figure to make things clear. So, A, B, C. Distance between A and B is 13 meters. And then BC is also 13 meters. Each of mass 100 kg. And there is a fourth particle here. Of same mass at a distance of 13 meters along the perpendicular bisector. So the force on this one is due to this B, that will be in this direction. Let me call this force F1 or F. And this force, we call it F1. And this force, the magnitude is again F1, but the direction is different. Okay, so the total force is vector sum of these three forces. So this one, the component here will be here, and the component will be downwards. But these two components will cancel. One is towards left, and this one will have a component towards right. That will cancel. And this is a 45-degree triangle because these two angles are same. Isosceles triangle. So total force on the mass P is due to this B, it's m square by this distance is 13 plus between this one is mass are same by this distance is 13 root 2. Distance has increased because of the hypotenuse. So the total, this is the total force on mass at point P. Forces like this. So 1 by root 2 and then into 2. So this is 1 root. So here it will become root 2. And 1 by root 2 is close to 0.7. So this is 1.7. So the force of the mass here is 1. This is one force, which is gm by 13 square. And this force is gm square by the distance is 13 root 2 square and the cos of it. That's 1 by root 2. And there is one more force here, so 2 of them. This is due to one mass A and second one is due to the C. So this is total force. So 1.69 approximately cancel 1.7. So answer is option B. B is the correct answer. So 3 masses are kept here. The distance between this is D, which is equal to 13. This is also D equal to 13. And the fourth mass is along the perpendicular bisector distance 13. So the force on this one is this force F1, which is gm square by d square, and this force F2, which is gm square by d root 2 square, and the component of it is F2 by root 2. It's 1 by root 2 and then twice of them. So it will become F2 into root 2. And that F2 is gm square by the distance square, which is d root 2 square. So simplifying, I get G, answer is 100G. So 1 by root 2 is 0.7. That approximation will be used. So that will cancel approximately 1.69.